Hello and welcome to BAC Talks. I'm absolutely excited to present to you the keynote speaker, Dr. Neri Oxman. In Dr. Oxman, we have a creative force, a great thinker, a talented designer, and also an institution builder who is really challenging what we think about practice and the disciplinary boundaries and addressing questions that are global in scale. For example, she calls herself nature's architect in service to nature and to rethink how we approach the world, particularly after what we have learned from the pandemic, how we work with materials and how we integrate the intelligence that is inherent in all life and in all materials for that matter, and how to work with nature in order to build a culture that is going to be sustainable in a very different way. And in doing so, she is reinventing and rethinking how we would build this new resilient world. Welcome to everyone. And I'm so excited today to present to you our keynote speaker, Dr. Neri Oxman. And first, I'm going to share with you some biographical information, and I'll make a personal introduction as well. So, hailed as a nature's architect, Neri Oxman is a designer, inventor, and researcher. Her design approach and philosophy, entitled Material Ecology, lie at the intersection of culture and nature, calling for the unification of the made and the grown across scales and species. Oxman founded the Mediated Matter Group at the MIT in 2010, where she established and pioneered the field of material ecology, fusing technology and ecology and biology actually to deliver designs that align with principles of ecological sustainability. Oxman became a tenured professor at MIT in 2017. She received her PhD in design computation at MIT in 2010, and prior to that, she earned a diploma from the Architectural Association in London. In addition to over 150 scientific publications and inventions, Oxman's work is included in the permanent collections of leading international museums, including MoMA, San Francisco Museum of Modern Art, Centre Pompidou, Mack Museum of Applied Arts, Frack Collection for Art and Architecture, and the Cooper Hewitt Museum, Smithsonian Design Museum as well. Her work has been recognized at the World Economic Forum, where she was named a cultural leader in 2016 and is a member of the Expert Network. In 2018, Oxman was honored with the Cooper Hewitt National Design Award and the Honorary Fellowship of by the Royal Institute of British Architects and the Contemporary Vision Award by SF MoMA. And one more thing I'd like to mention is the 2018 Design Award that she received from the London Design Innovation Medal as well. Now, she is the founder and CEO of Oxman. So, Neri, I'm so excited because it's wonderful to see you again, and always, I'm just kind of recollecting in 2008, I think, when we crossed paths, when you were the co-chair of the Association for Computer Design in Architecture conference, and I happened to be the president of Acadia at that time. So on both occasions, I happened to be president of something. We crossed paths.
That's wonderful. It's a pleasure to be here.
So, and I also wanted to just maybe broach one more item common to us, and that is our mentor, Bill Mitchell. And of course, Bill was your advisor and mentor, and so he was since 1995 for me. And my first book, Leading with Aesthetics at MIT, was inspired by him and his work. So just wanted to kind of pay tribute to our shared mentor, Bill Mitchell. So
I think Jane is listening. I hope Jane is. My warmest wishes to Jane, and I hope she can enjoy and channel the mentorship of Bill to us all. And I share your love and admiration for this wonderful man who has formed so many of us in his image. It's a pleasure to be here, to bathe in his vision.
Great. Well, with that, I will let you take off, please.
Okay, Mahesh, I didn't hear your last words, but I am assuming I can start presenting. So I'm going to share the presentation with you now. Let's see if you can see it, share screen. So here we go. This is particularly important year in the biography of our planet. Actually, last year, the year 2020, marked a crossover year when the mass embodied in the built environment, our responsibility, the architects, exceeded the biomass on our planet. Current building technologies and material practices, all the stuff that we do are the main culprit. And here we are, builders, makers, and creators of the physical environment at a crossroad, needing to decide which path do we take next. And the question is, can architects and designers of the built environment better themselves by bettering nature? Can the place where nature and culture, where the grown and the made intersect, create a multiplicity? What are the ways in which humans can continue to build for a sustainable human world, while at the same time committing to maintaining our planet sustainable? So operating at the intersection of technology and biology, we, my team and I, Mediated Matter, and now a new team at Oxman, we're calling for a fundamental shift in the way in which we design and construct the built environment, from consuming nature to augmenting nature. So shifting the discourse from the world of the machine, where we've designed static objects and buildings, discrete structures that were mass manufactured, to the age of the organism, where we're designing objects and buildings that are dynamic, that have a hierarchy of complex structures, that are mass customized, that are on-site fabricated, and so on and so forth. And to do that, we've created a body of work, or a field, an area of research we call material ecology, which is a design philosophy and also a scientific approach that explores and informs and expresses interrelationship between the built, the grown, and what lies in between, the augmented. And they're sort of placed against the backdrop of Lawrence Halprin 1960s Sea Ranch principles, the vision of the West Coast circa 1960. We seek to create sort of a viable synthesis of architecture, of the environment, and of our ideals. I sort of zoomed in here so you can see some of those principles, striving towards a nature-culture singularity, where we're seeking the augmented rather than the rural, naturehood as opposed to community, ethics as opposed to aesthetics, design empowerment as opposed to design control, and overall the enablement of connectivity as opposed to the preservation of access. And so you're seeing those two value systems sort of juxtaposed one against the other. And another sort of framework is this one to the right. The approach we were using for our projects brings into question Walter Gropius's 1919 manifesto, who proposed a radical vision for a new architectural studio or practice that erodes the distinctions between artists and artisans and offers a lens which embodies not only art and artisans, but here in our case, incorporates science, engineering, and technology with a capital S and a capital E and a capital T. So there are several contributing factors to our ability today as designers and architects to take action from a technology and science and engineering standpoint. And these innovations have to do with the computational tools that we're using, but also the fabrication tools that we're using. So for centuries, we've been taught to sketch and model and build in 3 static dimensions. And now, of course, we know that the natural world doesn't work this way. The natural world offers contexts which are dimensionally complex, dimensionally dynamic. And thankfully today, we have tools that enable us to incorporate these environmental dimensions like heat and light and humidity into the computational tools that we use. And here you're looking at some computational growth tools that we've used in mediated matter, tools that come from the world of computational geometry that can be used to derive generative systems for computational growth processes. So the search for growth begins with a computational growth, but it ends with fabrication. So here you're looking at a video that describes one of our inventions, one of our software-based technologies called data-driven material modeling that combines generative modeling methods with high-resolution multi-material 3D printing. And the generative approach is controlled using existing or dynamic data sets to drive the simultaneous generation of geometry and material information. So at once, you're looking at an ability to not only control the shape of an object, but also to control material properties, dynamic properties, etc. And current advancement in additive manufacturing enable the fabrication of these super geometrically complex and materially heterogeneous objects with very high spatial resolution in manufacturing. What you're seeing here is the ability to vary and heterogeneously modulate mechanical properties. And these advancements challenge designers and architects and engineers alike to move beyond shells, to move beyond the anatomy of a building to the physiology of a building, right? To move from the shape to the material to the properties of the building. So yes, we can vary the mechanical properties of objects. We can vary properties that are associated with water affinity, expansion. We can vary properties such as color and opacity, stiffness and softness, shape memory, swellability in this case, and of course optical properties as well. And that brings us closer to what I think of as the resolution singularity. That's sort of a moment in time where we're reducing almost to zero the dimensional mismatch between the grown and the made, the dimensional mismatch which we're seeing as architects between atoms and bits and even genes, the units of the biological world. So here I'd like today to present work that was created at Mediated Matter by Mediated Matter. Here you're looking at our alumni and the recent graduates of the group. Each of these individuals has contributed an immense body of work towards the mission of material ecology in projects and papers, inventions, patents, exhibitions, etc. And of course, scientific theses at MIT over a period of 10 years and more. And what I've done today is I've divided the projects based on a hierarchy of relationships between the grown on the one hand and the made, between the natural and the artificial, starting with biomimicry and moving slowly towards bioinformed systems, then towards bioengineered systems, then towards a kind of a singularity between the biological, between the natural and the artificial. So we're starting with systems that emulate nature, to systems that contain nature, to systems that synthetically interact with nature, to the moment where nature and culture collapse into one. So we'll start with biomulation, which is the closest to biomimicry, if I may. And these are some of the early projects you probably, some of you know, those of you who know our group, where we started to look into single material systems, moving away from assemblies and creating single material system objects, whether these are wearables or whether these are furniture devices, to optimize for mechanical conditions, or in this case for acoustical conditions, systems that are made of a single material system. So in this case, you're looking at 44 different materials with different preset mechanical combinations. One of our exciting collaborations with Stratasys, and here we're looking at 3 different scales that interact with acoustical properties to create a chaise for, this was originally designed for the Dalai Lama, to create a very, very calming and quiet environment by increasing the surface area and studying these high surface area to volume structures in the natural world, from the macro scale to the mesoscale to the nanoscale, but also looking at how we can vary the biochemical properties from stiff to flexible by varying the elastic modulus, in this case, of a mask that we designed for Bjork, where we explored, again, not a mask or a helmet that's made of an assembly of parts where you have steel and plastic and all these elements coming together in an assembly, but rather you have a single material system that can tune the physical properties and can recapitulate and augment or control the facial form of, in this case, of Bjork's face and the movement behind her face. And this was really conceived as a kind of muscular muscle textile, and designed and fabricated at the highest resolution that was native to the printer at that time. And some of these additional examples, we created a whole collection of them. So moving from biomimicry or bioemulation to biocontainment, how can we move closer to containing the natural world within artificial designs? Here we're moving from the differentiation of solids that interact between 2 or more materials to a relationship of containment. So here you're looking at a wearable device that is made of a single channel. It's 58 meters long. It varies in its diameter from 1 millimeter to 2.5 centimeters. And what we're doing is we're grading the mechanical properties, but also the optical properties, actually more so the optical properties. The transparency was graded regionally within the design to create areas where we could have photosynthetic microbes receiving light and producing sucrose. And so we have a biological system that is contained, a set of microorganisms synthetically engineered to create a symbiotic relationship between them. On the one hand, cyanobacteria, which lives and thrives off of light, especially in the transparent area. And then we have E. coli that can make useful materials such as sucrose, fuel, biofuels, and scents. And so again, this is a form of microbial symbiosis that is programmed into this quote unquote container designed and printed to not only contain, but also control the biochemical signals and the biological performance of these microorganisms within the wearable. Of course, you're probably asking, this is good and well for wearable scale, but what happens when we're moving from the wearable scale to the architectural scale? Well, at the architectural scale, we need to look for, if we want to do containment and we want to preserve energy and we want to create biofuels, we need to look for materials that are at once solid, strong, but also chemically inert. And one of these materials, of course, is glass. And in order to look at a kind of a containment relationship, we actually had to invent a glass 3D printing technology from scratch. And so here you're looking at a manufacturing platform that was designed to print optically transparent glass. And the tunability that's enabled by geometrical and optical variation, driven by form, by transparency, color variation, they could also drive and limit or control light transmission, light reflection, light refraction. And therefore, they carry significant implications for glass and in general for the containment of light and solar energy. This was our first printer, and some of the extrusion studies that we made, we of course got better and better over time, and we started printing at the product scale. We then went on to create a second 3D printer that was more sophisticated, moving us to the architectural scale. The computational framework that we used to generate each column's form was directly influenced by the constraint of the manufacturing platform and the structural system, demonstrating the ability to print a wide range of shapes that is determined by the desired mechanical properties, but also the optical properties. So for example, in this column, the higher the structural load, the greater the surface area of a column in plan view, a little bit like the Sagrada Familia. The greater the number of lobes desired, the tighter the turning radius required for their printing, and hence contributing to the geometric expression of these light effects that you're seeing here, the caustics. So this project really embodies that intimate relationship between the fabrication system and pushes it to its limit relative to the type of structural and optical constraints that we were looking to produce. We're now at a stage where we can create pockets and channels that can contain these synthetically engineered microorganisms at high resolution, similar to the wearable that you've seen, but this time at a building scale. Okay, I'm racing here, moving from biocontainment to biosynthesis. With biosynthesis, you're really looking to, the first project that I'll show is called Agohocha, really looking into how can we bring together digital fabrication tools and technologies utilizing materials that are unlike the previous examples where you've seen photopolymers, in this case, biopolymers, or materials that are entirely sourced from the natural world. So a bit of an environmental context here, and most of you are aware, but according to the United Nations Environmental Program, over 300, I'm sure it's more now, it's been over a year ago, so over 300 million tons of plastics are produced globally each year, obviously leaving harmful imprints on the environment. And less of 10% of this material is recycled. The rest becomes waste. It's dumped into landfills. It's dumped into the oceans. All the while, of course, plastic-based materials utilize raw ingredients that are extracted from the earth faster than they can be replenished and are processed through environmentally destructive means. And so we thought, we know that nature, from a very limited palette of molecular components that include cellulose and chitin and pectin, all the good stuff we eat, those are the very same materials found in trees and crustaceans and apple skins. Natural systems construct an extensive array of functional materials with no synthetic parallels. And we thought, could we use these very same materials to create products and even architectural structures that are entirely biocompatible? So this is sort of getting closer to the material ecology ideal of, come from the earth, go back to the earth, stay for as long as needed, and utilize programmable decay. And just as an example, you're looking here at the left at a crab shell made of chitin. Chitin and all crustaceans, are made from chitin. Chitin, for instance, is manifested in the form of very thin, often transparent dragonfly wings, as well as in the soft tissue of fungi and obviously in crustaceans. Cellulose makes up more than half of plant matter planet-wide. And these materials and the living systems that they inhabit outperform human engineering, not only through their diversity of functions, but also through their resilience, their sustainability, and their adaptability. And so we created an entire collection of these materials. We called it the Agohocha collection, offering material alternatives to plastics across scales with the aim of subverting this toxic waste cycle through the creation of biopolymer composites that exhibit tunable properties with varied mechanical and optical and even olfactory and gustatory properties, if you so desire to consume the building metabolically, so to speak. And so these renewable and biocompatible biopolymers leverage the power of natural resource cycles, but at the same time can be materially, quote unquote, programmed to decay as they return to the earth for purposes of fueling new growth. And Laia here is holding, one of these giant first parts we've printed that sort of that is tuned just in terms of the elastic moduli from near 0 to 40 megapascals, which was pretty impressive at the time we just started. And we realized that by enabling digital design and fabrication with biopolymers, we can aim to devise systems that incentivize the protection and the strengthening of ecosystems, while at the same time providing humans with a new frontier of design and production on the product scale, but by the way, also on the architectural scale. And this was 1 out of 3. We're currently at our 3rd pavilion, and they're getting better and better. But here you're looking at the first prototype. It stood 5 meters tall at the Media Lab, an architectural pavilion that was composed of the most abundant biopolymers on our planet. So a rough back of the envelope calculation, according to one of our PhD students, Nick, calculated 5740 fallen leaves, 6,500 apple skins, and 3,135 shrimp shells that were brought together to create this structure. And over time, with the evaporation of water, the pavilion's skin and shell composite transitions from a more flexible structure, relatively weak system, to a rigid one that can respond to heat and humidity and can be designed for heat and humidity. And so here you're looking at performance-driven design simulations that basically allow us to predict where do we need to place more or less material and what sort of variation of properties based on the type of, let's say, footprint of rain predicted in this area. So upon exposure to the rainwater, the pavilion skin and shell will and can degrade programmatically, restoring their constituent building blocks to the existing ecosystem and augmenting the natural resource cycle and enabling their synthesis. So what we've done here is we showed that shape and material composition can be directly informed by physical properties such as stiffness and opacity, by environmental conditions such as load, temperature, and relative humidity, and by fabrication constraints, degrees of freedom, arm speed, nozzle pressure. All of these things are combined in harmony, right? The nozzle speed defines the diameter of the jetting vector that then informs the structural performance of the building, et cetera, et cetera. So all of these parameters are interlinked across media, across scales, across material systems. When the biopolymer skins are submerged in water, the pectin-based elements will rapidly dissolve. They will allow the cellulose and the chitosan-based elements to deform. They'll degrade in a controlled, programmed fashion, and the structure's basic material components will be readily decomposed and reused by living organisms in order to fuel new growth. So through life and program decomposition, and you're seeing that on the right side, right-handed animation, where we're actually simulating the biodegradation, shelter becomes organism, organism becomes shelter, and we're sort of holding or promoting the health of the natural resource cycle by such means as promoting soil microorganisms and providing nutrients for literally growing buildings in the spirit of material ecology. So this project pointed towards a future where we subvert the industrial cycle of overproduction and obsolescence through the use of abundant natural materials, envisioning the ability to temporarily divert materials from healthy ecosystems, integrate them in human designs, and enable natural decomposition back into nature. So moving forward to biosynthesis, and here I think I have a couple of projects to show. We further asked, okay, we've used non-natural materials utilizing bio-informed algorithms and digital fabrication technologies. We've also shown how we've used natural materials per se using these digital fabrication technologies. What happens when we move past the material level into the organism or species level? such as silk, silk that's made out of, with the help of silkworms, honey that's made out with the help of bees, and so on and so forth. What are some of the sustainable and humane methods for harvesting and spinning and weaving in the next case, silk-based products and structures? And how can humans collaborate with other species to create new materials and structures without depleting natural resources? Some of you may know our first silk pavilion. Traditionally, silk is harvested by boiling the larva that is alive in the cocoon in order to extract the silk threads. We all know the silkworms are boiled in this process. And in stark contrast, we asked, again, this process we've invented in Silk One allows the silkworms to live and metamorphosize in relative peace, I would say in utmost peace. The base structure for Silk Pavilion 1 was created of 26 polygonal panels, as you're seeing on the right. It was made of silk threads that were laid down using a CNC machine. And once established, a swarm of 6,500 silkworms was positioned at the bottom rim of a scaffold. They began their work. They spun flat non-woven silk patches, and they locally reinforced the gap across the CNC deposited silk fibers. So we've attempted to emulate this process in Silk Pavilion 2, and we discovered that, and here you're looking at a computational simulation that explores the impact of static and stepped and continuous motion over silkworm spinning behavior, but you're also looking at the impact of light, for example, on the silkworm's behavior. So in our second pavilion, which we've designed for Paolo Antonelli's Material Ecology exhibition in the Museum of Modern Art, which was on show last year, unfortunately during COVID era, the fiber density across the surface area of the structure varies as a function of local environmental factors, such as the direction, the duration, the intensity of heat and light, as well as the topology of the kinetic hyperboloid that is designed to guide the movement of the silkworm, which you'll see in a minute. And these factors, these environmental factors can affect the silkworm's movement and spinning, resulting thereby in modified thickness of the silk layer that produced. So there now becomes or emerges these complex relationship between the organism, between the material system, that is the fabrication output of the organism, and of course the robot itself. The second pavilion, which is much larger than the first pavilion, was constructed using, actually constructed in a horizontal orientation with mechanical top-down kinetic manipulation that enabled constant clockwise rotation of a mandrel, sort of a giant clock, that facilitated the silkworm's upward spinning motion. And we simulated this process. We created several computational simulations that explored the impact of these static, stepped, and continuous motion over the silkworm spinning behavior. And we attempted to optimize the rotation of this robotic mandrel such that we will be able to enforce or enable roughly equal pressure across the surface area, equal tension across the surface area of the pavilion. Again, what's so special about our group's work is that I don't know that there's a single project we've created for which we didn't create the technology, and these technologies are created literally from scratch, right? We're not buying off-the-shelf parts and hacking them. They're created mostly from scratch. Here, the pavilion's primary structure and the sawbill knit, there was a sawbill knit scaffold that were stretched with a cable system, and it gave it its physical properties as a kind of an intermediate knit yarn layer that acted to support the silkworms. The little holes, which you're seeing, release some of the tensile stress in the structure. They resulted from chemical reactions between the silkworms' excretions, actually, and the underlying yarn. And these structural forces are influenced biochemically, and they're expressing the metabolic footprint, if you may, of the silkworms' fluxes and flows. The pavilion is made of 3 interconnected layers. The innermost primary structure was comprised of a one-dimensional braided steel wire rope The secondary was a two-dimensional fabric, as you're seeing now, and the tertiary three-dimensional structure was biologically spun with the help of 17,532 silkworms that were sourced from Tirolo, Italy, in one of the most extensive silkworm rearing facilities in Europe, in the region of Veneto, where the tradition of sericulture and silk manufacturing blossomed during 12th century Renaissance. We were very, very lucky to work with Silvia's team in the sericulture, Silvia Capellozza in the Sericulture Institute there. And so 10 days of co-creation among silkworms and humans in a huge, gigantic robotic loom resulted in a structure made of silk threads longer than the diameter of planet Earth. And this was installed at the Museum of Modern Art, again, for Paola Antonelli's exhibition, Mediated Matters monograph show. I show this image because it's dear to our heart. These are female silk moth laying eggs with circular vessels in Silvia's lab. And it sort of got us to question, how might we invent technologies that enable co-design and co-manufacturing, cohabitation, not only between humans and buildings, but also between humans and other species. These are fertilized silkworms' eggs that are preserved in cold storage. And again, sort of questioning the 6,000 years of sericulture and proposing that perhaps, just perhaps, the Silk Lab is more sustainable than the Silk Road. This has immense implications, obviously, for wearables. If we can reinvent an entire industry without boiling silk cocoons, but rather co-fabricating along with them to reinvent the wearable and silk industry, that would be wonderful. Sericulture has been criticized by animal welfare and animal rights activists due to the fact that the processes of harvesting the silk from the cocoon obviously kills the larva. And in the textile and silk industry today, silkworms are exterminated while in their cocoons and the silk is dissolved. And what we've showed is that the process that we've created allows a single silk filament to be unrolled from the cocoon without disrupting the life cycle and the development of the organism over its life cycle. And as the Silk Pavilion demonstrated, but any other architectural tent-like structures or wearables structures can influence the silkworms to spin in sheets instead of cocoons, thereby producing the same quantity of silk without boiling the cocoons. So this, again, a project that was very, very close to our heart, illustrated how these compact and unique insects can act not only as living looms, but as co-designers collaborating with humans. The next project looks not at silkworms, but at melanin. And the sort of the context for this project is really the state of biodiversity on our planet. And as you've seen in the first slide, and as I've pointed out previously, biodiversity in planet Earth is under momentous threat, even for those of you who don't believe in the sixth extinction. Extinction rates are today estimated at between 100 and 1,000 times their pre-human level. So we have been at Mediated Matter, we've been in search for materials and chemical substances that can both sustain but also enhance biodiversity across living systems, and have so far endured the perils of climate change. One of these materials is melanin. Melanin is a naturally occurring chemical chain. It gives all living things their pigmentation. We call it the color of life, the pigment of life. It's one such substance that can sustain and enhance biodiversity, not only the genetic, but also the species and the ecosystem level. And an identifying feature of all living organisms, believe it or not, it exists in all kingdoms of life. Melanin represents unity in the diversity of life on Earth, and is clearly linked to biological survival throughout the ages, and by the way, way before humans showed up on the planet. So it's 307 million years old. Its value for human health and for culture across regions, across environments, it's priceless, and obviously its impact in the age of climate change is key to human survival. We know it's a biomarker of evolution, and the substance that defines the color of hair, feathers, skin, and eyes, again, across kingdoms of life, again, way before humans showed up, is at once ancient but also modern. We know that we can, melanin is found in fossils dating from the Mesozoic era, but we know that today we can chemically synthesize melanin using modern techniques. It's one of the most resistant, heterogeneous, and pervasive pigments found, again, across all kingdoms of life. And in addition to the critical role it plays in providing protection from UV radiation, it serves a wide variety of functions: mechanical protection, energy harvesting, cell growth, metal binding, thermal regulation, protection from oxidative stress, and I can go on and on and on. So in this project, we addressed, and we also speculated upon the designer's ability to chemically synthesize this pigment of life as a functional material and program the interaction across scales, across species, for the betterment of biodiversity. So melanin, as you can see in these slides, we've synthesized it in our wet lab. We have a wet lab at the lab. It's a BL2 wet lab. And we ourselves synthesized it through a reaction between an enzyme that is found in mushroom called tyrosinase and the protein building L-tyrosine, as you can see in the right. And the pigment can be extracted from bird feathers, cuttlefish ink, and our own hair. All right, and then it can be purified and filtered in a series of steps. And over the past years, we've developed methods for the design of structures that can contain biological substances across scales, but also across phases, solids and liquids. As part of the basic research behind totems, and this is a project we've created we started with a project we created for Paolo Antonelli's show Broken Nature, and we created a series of vessels that feature a single connected channel that was filled with liquid melanin, and these vessels display a wide range of colors and absorption spectra from light yellow to dark brown that are designed, again, to protect from UV radiation. The channels within these vessels have been computationally grown, 3D printed, and biologically augmented to create pockets for the liquid melanin to reside in, with channel diameter ranging from millimeters to centimeters. So the first of its kind biologically augmented facade, this structure was designed to protect endangered species in the place where Nelson Mandela once stood. The project was endorsed and supported by Design Indaba and the Nelson Mandela Foundation. And of course, through this investigation, and it's still ongoing, we question our ongoing relationship with biology, ecology, and of course, with natural history. And finally, we reach the singularity. And sort of we here in the last project, which is called Vespers, we looked at a collection of death masks that we've designed with the aim of creating living products, a death mask that becomes an alive mask, a living product. It was a very large collection that created a large body of scientific inquiry and actually a new class of materials that we've termed hybrid living materials, HLM. All the papers are online. It was a collection of masks that explores what does it mean to design with life. And it started with these masks that we've computationally designed and digitally fabricated. It started with a relic of the death mask. The death mask is kind of a contemporary living device. And the collection embarked on a journey that started with an ancient typology that is today not even useful, but culminated with a new technology, a novel technology for the design and digital fabrication of adaptive and responsive interfaces at the product scale and the building scale, and you'll see what I mean in a minute. But this first series that you're looking at featured the death mask as a kind of a cultural artifact. The second series featured the mask as an enabling technology. The third, mediated between the two, where we started with a conceptual place and we ended with a tangible set of tools, techniques, and technologies where we're combining programmable matter and programmable life to recapitulate the colors and the patterns of the ancient relics. So we start with culture, we end with nature, and we sort of teach nature how to recapitulate these highly beautiful and highly cultured patterns. again, the nature and culture singularity. So in this first series, driven by a parametric grammar, we used polyhedral meshes that evolved over time into subdivided surfaces using an algorithm that emulated cellular division. And here, and again, this is taken from our website, all the materials are online, you're looking at a visual representation of the generation process meshes that were generated for the performance evaluation and variations with 2 materials and with 3 and 4 materials and so on and so forth. But the main point here is that using a very minimal set of rules, the series generated a wide array of patterns and colors and shapes and schemes, and the implementation of in this case, Stratasys full color multi-material 3D printing technology that really enabled the creation of objects that match the variety and the nuance of these ancient arts and crafts. Computational design was integrated with additive manufacturing and with synthetic biology to digitally fabricate these objects and to direct microorganisms to produce pigments that, again, emulate the colors of the first series of the collection. And here we leverage 3D printable bioactive materials to spatially template the biological response of living microorganisms. So we were able to use computational and digital fabrication tools and customize them to direct the growth and the expression of the microorganisms contained within the masks. And as well, we were able to incorporate chemical signaling within the digital fabrication platform. So this is really where the core, I would say, the cutting edge skills of our group really came to express themselves, where we truly brought together the best of the atoms and bits and genes into a project that leverages additive manufacturing of bioactive materials to spatially template biological response of living microorganisms. So computational and digital fabrication tools were highly customized to direct the growth and expression of these microorganisms that were contained within the masks. And the research, again, which we call hybrid living materials, enables the computational design and fabrication of consumer products and freestanding structural materials, from cosmeticals to antibiotic production to wearable devices to smart packaging to surface coating that can detect contamination, to environmentally responsive architectural skins, and so on and so forth. So the research really offered a new space for biological augmentation across a wide breadth of application domains that leveraged both resolution and scales. So these final masks, now living things unto themselves, were featured patterns that were generated by genetic regulatory signals distributed according to the spatial logic provided by the second series and according to the patterns provided by the first series. So the project allowed us to push additive manufacturing even further, and you can see these are some images of the masks from the second series and some zoomed in views to just show the detailing and the tailoring of these wearables, both to the body and to the environment which they inhabit. I will stop here. A fun little slide from our previous synthetic apiary, which looked into not silkworms, but bees, and coexistent with bees and the generation of comb. We're currently working on a new project that looks specifically into bee combs to be published soon. And just a final word of gratitude to my team, the Mediated Matter Group, but also to all the students who shared a studio and a workshop, and indeed shared a wet lab to push and promote a new area, and indeed a new era in the future of design and architectural production that looks at the natural environment and sees the nature as an equal partner in the creation of the built environment and its many products. So here's hoping to a better synergy and harmony between what we make and what we grow. And I will end here and turn off and connect back with Mahesh.
All right. Neri, that was so inspiring, and it's extraordinary. It's just breathtaking, the range of collaborations, the kinds of original technologies developed. I think you've talked about this quite often, about really going beyond these disciplinary boundaries and building a practice that can only be done through design and by designers. So I wanted to connect those three things there, if you could talk about that.
Sure. So it's interesting. If you go to our website online, you'll see that each project is actually classified through 3 or 4 Ps, and I can't remember. We're constantly sort of shifting, where we start with position, process, product, and policy. And these are sort of the 4 Ps that we're now utilizing in our new practice in Oxman as we build a new team. And the aim here is that for every project that we take on, there's a position, there's a philosophy that relates to the current state of the art, environmentally and otherwise, technologically. And there's a product that is intimately linked to the process. Again, I think I mentioned it once in my presentation, but there's not a single product that you've seen in the presentation for which we have not invented a new process or a new technology. And the portfolio of invention is rich and deep and wide. And then that technology is then utilized to push forward changes in policy and question our value system. And so I think, when we consider the future practice, not only is it incumbent upon us to move beyond the drafting board and indeed the computer and indeed the printer and indeed the laser cutter to tools that are bio-based, bio-informed, and bio-enabling, but it is also extremely important that we keep in mind how might these technologies make an impact not only at the level of a singular commission, but at the level of policy change, right? At the level of how do we treat the silk industry? How do we consider the concrete industry? What kind of ethical code? And this is where the value systems that I introduced in the beginning come into play. So values and technologies are incredibly important to the architectural practice of the future. It is no longer about building signature buildings alone or only.
So, Neri, there are a few questions in the chat as well. I'm going to talk about one question is about lab to field. I know that your lab has done both, work in the lab and work in the field. So would you talk a little bit about your experiences and thoughts?
Yeah, it's interesting. We've moved from the field to the lab. We've utilized biocompatible, biodegradable, bio-based materials. We've engineered them. We created new technologies to process them. Less so from the lab back to the field. And that's sort of where our crossroad currently is. We're starting a new practice where the idea would be then to take these projects and buildings and structures from the museum, from the gallery, from the lab, and into the real world, and truly test them against the real world. So you're finding me at a crossroad, as well as my team and our work, and we are all feeling the positive pressure and the inspiration to bring the work from the lab and back into the field in a real way.
Yeah, I just wanted to credit that question was from Stephen Fallon, one of our students. Great question. And another question is about scalability. And I think scalability, you've talked a lot about this, but I'll let you take that question and run with the notion.
Yeah, I mean, right. So when you think of scale, scale is not only about size, it's about not only scaling in size, but also preserving complexity. There's a reason why nature operates in the scale in which she does. And there's a reason as well for we, starting at 1850, operate in the way that we do, well, that is because we've inherited the legacy of the Industrial Revolution. And since we haven't stopped or taken a moment to question that legacy and reinvent it, which is what we must do now, all of us. Scale. Well, you've seen that some of the projects that I've shown are very challenging to scale up. And those are projects, again, materials are the bottleneck. So for the photopolymeric-based projects that I've shown, creating an entire building out of these digital materials is practically impossible, but also not environmentally friendly at all. So again, some of these projects served the role of creating new knowledge and new science and new computational methods, but the material was, again, photopolymer based. But in the materials that are starting to be more bio-based, the biopolymers that you've seen in Aguoja, yes, we can start thinking about tent structures. Yes, we can absolutely think about the product realm. We can absolutely think about wearables. And when we move into glass, into materials that are structurally strong, chemically inert, we can start looking into translating some of these principles which we've gleaned from and learned in the previous project towards larger scales, building scales. And again, the vision behind the glass printed columns was, can we create a Centre Pompidou without parts? Can we create a building without multiple systems that each serve a different function, structure, environmental properties, optical properties, solar energy, circulation, but rather create one or much fewer material systems that not only enable the same kind of functionality, but also augment the natural environment. They give back. They're maybe CO2 sequestering. They are, maybe they can harness solar energy in ways that currently were not possible. The beauty about the glass printer, and just one more word about scale, is that because we're, unlike traditional glass blowing techniques where the surface area is mostly smooth, whether it's pressing or blowing. In this case, with printing, we can control interior and exterior geometrical features, and therefore we're creating an optical lens. If we can create an optical lens, of course, we can contain direct control the refraction and reflection of light and optical properties across the surface area. And so we're creating an optical lens that can harness solar energy. Big deal when you scale that up in the urban context, for sure. I haven't shown the concrete printer, but we did build a compound arm that was recently acquired by NASA to print on extraterrestrial terrain using moon regolith or Mars regolith, which brings us into scale. But again, in this case, we've tested with foam and concrete, and the intelligence in the project is in the scaling the arm, the robot, as opposed to the material. So I think with scale, it's tricky because you can look at materials as the bottleneck, then you can look at algorithmic designs associated with a robot as the bottleneck. But when you bring the two together, it becomes really, really challenging. Hopefully, you'll see more of that in the context of the new practice.
Absolutely, and that was a great question from Elena, and she's joining us from TU Dublin. Thank you for joining us.
Hey, Elena, thank you for your question.
So that's great. And wanted to talk about practice a bit more, Neri, because, as you know, BAC is known for practice integrated education, which is what you do. And that is fascinating. So I wanted to see how practice innovation, as to how you do practice, needs to be really rethought as you're doing, and what we can learn from that.
Yeah, so absolutely should be rethought. Again, the automobile industry and the architectural industry are still far behind what we can do with jellyfish, right? So with biomedical research, we're moving so quickly with projects that focus on brain health and longevity. But with regards to the built environment, we're still way behind, and that is because, again, we are used to utilizing technologies and traditions that we've inherited from the Industrial Revolution. To enter this new world, we need to equip the new practice with new spaces. The new spaces should include, every architectural practice should include a wet lab. Yes, every architectural practice should be able to test materiality and materials, not in the timeline of or the life cycle of a single building, but of a city, and not of a modern city, but of an ancient city. Adobe brick construction, there is a reason why the urban areas that have been designed with Adobe brick construction have sustained the environmental perils and the test of time, and have outlived steel and mortar and brick and construction technologies. And that is because of the wisdom of the craft. And now we have the opportunity to work with materials that come from our environment, but we have the opportunity to augment these materials with intelligence that can give back to the environment. So the new practice has new types of spaces. It also has new types of disciplinary knowledge that we're bringing into the practice. Every architect, in my opinion, should take a synthetic biology class. Every architect should take biological engineering courses, et cetera, et cetera, et cetera. So the syllabi and the syllabus needs to completely be rethought. And one inspiring example is Design Across Scales, which I had the honor and pleasure of teaching with Mi Jin-yoon, now Dean at Cornell, that focused exactly on that pedagogy.
Quite extraordinary. And that is a perfect conclusion, Neri, to, I'm pretty sure, a session, and this is recorded, so people are going to watch. Now we have something like 545 people who have joined us today, and many more are going to watch. And thank you for offering to come back another time to sit down.
Thank you so much.
Yeah, and we are very grateful, really, absolutely. When I reached out to you, you were so gracious and so enthusiastic in coming and speaking with us. So we appreciate it, and wish you all the best with the new practice that you're launching, and looking forward to talking again in the near future.
Thank you so much, Mahesh, and thank you to the BAC community, which I still so love and adore. And I look forward to conversing and continuing the conversation and continuing the interaction.
Absolutely.
Thank you so much.
Thank you. Bye-bye. Wasn't that an extraordinary and inspiring presentation? I think there is a lot that Dr. Oxman has presented today, shared with us, the enormous amount of work that she and the collective that she has built over the last decade and a half, and longer for that matter. She has talked about how it is important to understand the processes of nature and to learn from those processes, and to be able to integrate them into the culture. So the nature-culture integration is fundamental and essential to all of her work. And also the notion of collaboration that crosses disciplinary boundaries. I think we have seen that in an ample evidence of that in her talk today. How she worked with biologists, engineers, sericulturists, artisans, and material scientists. In doing so, she has really invented this new field, if you will, called material ecology. And she talks about how she could do that only because she is a designer. And that being a designer is at the heart of all of her work. And that perspective, the ability to seek the problems, she talks about this quite a bit, and not necessarily take the problem as it is given to you as defined, but to seek the problem, to pose the questions, and go where the question leads you, as opposed to any preconceived notions of a product or a result. So that is quite extraordinary that we need to, I think, understand and take it into our education, into our practice, and particularly at the Boston Architectural College, where we are known for integrating practice with academic learning. And I think we see a great model in Dr. Oxman and her practice and her work at the Media Lab at MIT, that we really need to rethink and reinvent what practice means. What is the purpose of practice? how do you structure it, and how do you actually define who you're going to serve. And as she said, serve nature and work at a scale, or rather work at different scales, that there is no one particular scale where you could be effective and engage and contribute to the world. And the notion that she has invented technologies, that she is now taking them into practice to scale up, is quite extraordinary. Think for a moment that it is an equivalent to, let's say, I were to invent a computer and then use that computer in order to design something and build something using that machine. So that is the kind of analogy I would use to kind of technologies that she and her lab and teams have invented. And that, I think, is absolutely unique and ingenious. So there is a lot more to be learned, and I thank you for joining us today for this extraordinary treat. And I'm sure that this is not the last time that Dr. Oxman will be speaking with us. So I look forward to inviting her back and have more conversations and engage her with our extraordinary community of students, faculty, staff, alumni, and friends. Thank you.